So a volcano is an object on the Earth's surface that's shaped like a cone, and what comes out of a volcano is either lava or pyroclastics. Lava typically just flows out of a volcano, whereas pyroclastics typically explode out of a volcano. Deep down inside of a volcano, you have a magma chamber, also called a pluton. It's connected to the crater at the top of the volcano through a factors that affect the nature of a volcanic eruption would be magma temperature, also followed by magma composition. So the hotter the molten, the less viscous it is, which means more runny. And also the less silica, the more runny it would be. And so the opposite would be more silica, would be more viscous or thicker. And so we relate back that to Bowen's reaction series. So felsic means more silica, so it's thick, and mafic means less silica, so it's runny. And remember that viscosity is the resistance of a molten to flow. And typically the more viscous it is, that the molten is it just kind of sits down inside the ground because it's so thick, so it can't run, so it just builds up and builds up and builds up, and it eventually explodes. So when I think of volcanoes, I think of silica, and so high silica I relate to felsic, which is your granite and rhyolite brother-sister, and then of course you have diorite, andesite in the middle with intermediate, and then you also have gabbro and basalt with low silica, which is your mafic compositions. So typically if I heard that there was a lava coming out of the ground and it was basalt, then I would know that it was probably going to be runny or gentle, as opposed to rhyolite, which is high in silica. It would be more explosive for sure. There's three kinds of volcanoes we have on our planet: shield volcanoes, composite volcanoes, and ash and cinder volcanoes. Shield volcanoes are really wide, they're really easy to climb with a low slope, and they're only made of lava. And so as a result, we can connect that to mafic, so gabbro and basalt, and so we would expect a basaltic lava to come out that's low in silica and low viscosity, so it would be runny. An example of that would be Mauna Loa and Kilauea on the island of Hawaii. Ash and cinder is the smallest volcano of all, really, really narrow, 30 to 40 degrees, so quite a little bit of an issue to try to climb one of those, but because they're so short, where they don't really go so tall in the sky, you wouldn't have to climb them for very long. The only thing that comes out of an ash and cinder volcano would be pyroclastic material, so you could get some scoria, and you could also get some vesicular basalt, that kind of thing. You can see an ash and cinder volcano, Sunset Crater in Arizona, or Paracutin in Mexico. Composite volcanoes, they're the scariest. They're crazy. They're typically not as wide as a shield, not as narrow as an ash and cinder, but they're definitely the hardest to climb with the highest slope. They alternate back and forth from a lava flow to a pyroclastic explosion. So that's why you can get various different types of rocks in a composite volcano, because it really depends if you're talking about the pyroclastic explosion or the lava flow. Most famous ones would be like Mount Vesuvius in Italy or Mount St. Helens in the United States, but they are by far they actually 3 to 4 kilometers high, and they can be pretty wide too, roughly around 20 kilometers. So as you can see here, a shield volcano is about 150 kilometers wide and can actually go up to 9 kilometers high. So no doubt shield volcanoes like Hawaii are the biggest, and Iceland and Surtsey, by the way, they're the biggest volcanoes on the planet, typically made of lava only. Composite volcano like Mount St. Helens, you can see the alternate structure, so it kind of alternates back and forth from ash and cinder to lava. About 15 to 20 kilometers wide and 3 to 4 kilometers high into the sky. Ash and cinder, really small, only about 1.5 kilometers wide and about 300 meters high. Only pyroclastic materials, so that's like your Sunset Crater or your... This graphic just gives you a perspective of the angle and the width and that kind of thing. A lot of times with the shield volcanoes, you got to remember they form on the ocean floor, like Hawaii and Iceland, so you don't typically get to see the whole volcano because it starts on the bottom of the ocean floor. And I say that because shield volcanoes are the biggest volcanoes on planet Earth. When we talk about gentle eruptions now, we're back to silica, and so we're talking about low silica, so low viscosity and going to be really runny. So typically we get that at divergent plate boundaries, which we think about like seafloor spreading at ridges. or typically hot spots underneath the oceans. It would have to be a mafic molten to make it runny because of the low silica. The other place would be a lava flow, which we associate with lava plateaus, which we associate with fissure eruptions, which will come up soon. And so typically you get flood basalts from a lava plateau, and you get shield volcanoes at divergent plate boundaries and hot spots under ocean. Here's just some of the locations where we get those fissure eruptions on our planet. You can see the greenish brownish area. So the one that would be closest to St. John's, Newfoundland, that you could actually visit would be the Columbia River flood basalts in the western United States. Explosive eruptions I relate to convergent plate boundaries. So anytime two plates come together, one plate loses and gets subducted down into the asthenosphere. So think about subduction zones when you think about explosive eruptions. Typically get ash and cinder volcanoes, but definitely composite volcanoes that are very destructive. The other thing that I wanted to say is every time you think of explosive eruptions, you need to think of Yellowstone. And Yellowstone National Park also forms from a hot spot. And in this particular case, the hot spot, similar to Hawaii, however, this time it's explosive because the volcano is under a continent, or the magma chamber is underneath the continent. And continents are felsic, high silica, and thick. Here's a picture of Mount St. Helens in the background, a composite volcano, and also in the foreground you can see the Columbia River basalts, which form from a fissure eruption. Nice picture of a pyroclastic explosion, a lot of ash and cinder there. Yet, not easy to breathe. Watch for aerial debris like bombs and cinders and stuff coming down out of the sky. Definitely explosive, so we know high silica. Here's a picture of a composite volcano, and the biggest thing that I wanted to point out in the composite volcanoes, you can see that it alternates back and forth from lava to pyroclastics, and we've already talked about the width and the height and examples around the world of composite. So this is just a little graphic of plate tectonics, and just to be, I guess, a little general here, this would be a divergent plate boundary, and as you can see, the two plates are actually going apart. Lava's coming up and pouring out onto the ocean floor. So in this area right here, we get a mafic lava, low silica, runny, low viscosity. So this is where you would get your shield volcanoes. This is a completely different boundary here. You can see a subduction zone. So the two plates are coming together and one's losing, and it goes down and it melts, and then the magma burns its way up through a continent which is felsic, high in silica, and thick. And so that's where you would get your Mount St. Helens or your Mount Vesuvius. So they would be your really, really, really explosive ones. This is just a lava plateau here that you can see. The fissure goes really deep down and connects all the way down here, so the molten that comes up is just typically mafic, so it's runny, so it just runs over the ground, and eventually layer after layer you get a lava plateau build up. So shield volcanoes got the least amount of silica. It got a low viscosity, so it flows. Gas content is low, and it's pretty quiet, free flowing, and you get shield volcanoes at divergent plate boundaries. Ash and cinder got the highest silica. It explodes. It's really thick. Lots of gas. Very, very violent and explosive pyroclastics only. Typically mostly found at convergent plate boundaries. Composite volcanoes in between the two in terms of silica. The viscosity also in between, and it flows and explodes because it alternates back and forth. So you get a quiet, free-flowing lava flow followed by a violent, explosive pyroclastic explosion, and that's a convergent plate. There's two types of lava you typically can get. You can get a ropey lava, which is called pahoehoe, and you can get a jagged, angular, sharp type lava, which is called ha-ha. And I'll show you a couple pictures of each on the next slide. One thing I wanted to say here is that the most common rock that you would get at a shield volcano is basalt. So that's one that you would totally get on a public exam. For ash and cinder volcanoes, I would mostly relate that to rhyolite, and sometimes you could get like scoria or pumice, which is volcanic glass. A composite volcano, I'm going to take this out, this is a typo. Composite volcano, think of rhyolite because that's your felsic lava rock, and then we'll even go back to like intermediate lava rock and think about andesite in the Andes Mountains. I mean, you have a lot of composite volcanoes in the Andes and in the Rockies. So here's a picture of your ropey pahoehoe on the left and your jagged aha on the right. Now we're going to talk about a different scenario. So when we first realized that we had plates on our planet, 21 plates, most of the earthquakes and the volcanoes were all around the plate boundaries. and then there were a couple of exceptions found. So exception was found in Hawaii, and one exception was found in Yellowstone. And J. Tusa Wilson discovered these things called hotspots intraplate, meaning within the plate and not on the boundaries at all. Typically how these hotspots work, and a hotspot is just simply a magma chamber that randomly appears underneath a plate. The hotspot doesn't move, but the plate does. So the plate moves over the hotspot and burns holes into the plate. So because the hotspot don't move and the plate do, you get a little pattern of volcanoes on the surface, and you can actually use that pattern of volcanoes to actually tell which way the plate is actually moving. The biggest difference between Yellowstone and Hawaii would be the fact that Yellowstone, it burns through a felsic continent, so the silica is high, which makes it explosive, and for Hawaii it just burns through a basalt ocean plate, ocean crust, which is just basalt mafic, so it's typically more runny, so the eruption is more gentle. So as you can see here, the magma chamber is there, that's the hot spot, it doesn't move, and the plate's moving to the right, and you can see these little volcanoes on the surface. As you move away, the volcanoes that are not currently on the hotspot, they get older as you go away. And so that applies to Hawaii, of course. And in this particular case, the volcanoes in Hawaii would be shield volcanoes due to the mafic composition. When you have a continent involved, it's completely different. So because because Yellowstone comes up under a felsic continent with high silica, not much happens. So if you were in Yellowstone right now, there's no real eruption taking place. It's just building a building, but when it goes, you can be sure that it's going to be explosive. So as you can see on this particular graphic, this is the volcano that's currently under the hot spot, that nothing's happening due to this felsic continent, thick molten down there. But you can see that we've had a series of volcanoes that have went off in the past. So we can tell that the plate was going more west and now is going more southwest. And so we can see the direction of the plate as it moves over the stationary hotspot. Lava plateaus. So a plateau is something that's really high, and lava is lava. And so a fissure is just a really deep crack that goes way down to the mantle. And this mafic molten comes up to the ground, real low silica, really runny, so it's basaltic. And when it comes out, it just pours and flows for a really long ways, making a lava flow. Or a basalt flow, or a flood basalt, whatever you want to call it, and then it usually cools and solidifies until the next eruption, and it just happens, and you get layer by layer by layer on top of each other until you actually get what's called a lava plateau. Short-term effects of a volcano: material can block out the sun. You can have some short-term cooling, maybe like a few months to a year. That's typically colder than normal. You can disrupt air travel since planes can't fly through air with volcanic pyroclastic debris. The volcanoes can create new land. Now, I actually see that as more of a long-term positive benefit as opposed to a short-term one. A lot of times you can get a lot of damage, like property damage and road damage. That's more short-term. It can be fixed. Naturally, death to organisms should be in the long-term list because that's certainly a long-term effect. A lot of times these volcanoes send out a lot of dangerous gases like sulfur dioxide and nitrous oxides, and typically goes up in the sky, mixes with water, and when it creates acid rain, and acid rain can be really bad. So just some graphics here. You can see, bottom right, you can see that was definitely an explosive volcano and buried the church and things in that area. We all know about Mount Paley before and after, a devastating one. The top two graphics typically would relate to Hawaii. So the lava pours out in the ocean floor, creating condensation, and you can see lots of pahoehoe up in the top right corner. Gentle flow, but it just flowed over those vehicles by the looks of it. Long-term effects, you still have the acid rain issue. Volcanoes positively create really fertile soils, which is really good for agriculture. For example, like Italy, known for their olives, lemons, and grapes to make wine. That's a good thing. And but the biggest one is that volcanoes give out gases, and so we always talk about global warming and how humans are causing it, but volcanoes are a natural phenomenon that actually give out carbon dioxide and water vapor that are both greenhouse gases that lead to global warming. So volcanoes are responsible too. The biggest issue of all is number 4. And so, depending on which volcano goes off, how explosive it is, if more than one volcano goes off in, a relatively short period of time, the size of the eruption, how much pyroclastic material goes up into the sky, we could potentially cool the globe and send ourselves into an ice age and block out the sun. And naturally, if the sun goes, then all plants that do photosynthesis goes, and then basically we have an entire collapse to the food web. So that's really scary. Certainly a way that we could go into extinction as humans, no different than, you know, what happened to other species. You know, like dinosaurs went extinct due to a meteorite impact. Trilobites went extinct to a breaking up of a supercontinent called Pangaea. But, you know, the volcano option is certainly another way that we could have a mass extinction. Different careers that you could do, or I guess go work towards if you're interested in volcanoes, is listed here on this slide.